Alright, so far we have talked about ordered sets, the greatest lower bound property and the least upper bound property, showed that these two are equivalent. And in the context of this course, most importantly, we have shown that the set of the rationals does not satisfy either property, right? So the set of rationals is an ordered set which does not satisfy either the greatest lower bound property or the least upper bound property. What this means is that there exist subsets of the rationals which are bounded from above but do not possess a least upper bound. Similarly, there are subsets of the rationals which possess a lower bound but not a greatest lower bound or infimum, right? So this is what we have shown, and I alluded to the fact that we construct the reals as an extension of the rationals in such a manner that the extension does in fact satisfy the greatest lower bound and the least upper bound property. Okay, so to state very clearly what the set of reals is, I need this concept, this abstraction of ordered fields, which I'm going to introduce in this video. Okay, so before I define what an ordered field is, I first need to tell you what a field is. Okay, so let me define that first. A field is a set with two operations, addition and multiplication. Addition is typically represented using our familiar plus sign, and multiplication. And it should satisfy the following properties. Okay, so you need a set, you need two operations, addition and multiplication, defined on the set, and these operations should satisfy a whole bunch of properties which I'm going to list now. And if this is all true, then that set and the associated operations is said to be a field. Okay, the first of these first set of axioms relate to addition, so let me label them as such. So the first axiom is that if I take any two elements of the field, the addition of those two elements yields another element also within the field, right? In other words, the field is closed with respect to addition. That's the first property. The second property is that x plus y must always be equal to y plus x for all x and y in the field. Right? This is the commutative property. So the addition operation that is defined on the field must be commutative. Okay. The third property is the associative property. Right? What does this mean? It means that if I first add x and y and then add the result to z, I would get the same answer as I would if I added x to the sum of y and z, right? So in other words, the order in which one performs addition is irrelevant so far as the sum is concerned. So that's the third property. The fourth property is in fact the existence of a special element called the additive inverse, also called, not the additive inverse, the additive identity. There exists an element called 0 in F such that 0 plus x equals x for all elements of the field. Okay, so there should exist this special element, I'm just labeling it as 0, which satisfies the property that if you add 0 to any element, any other element, you will get back exactly the same element. Okay, so that's the fourth property. And the fifth property is the existence of an additive inverse. To every x, there exists another element which I'm going to call minus x also in f, such that x plus. Okay, so the properties that addition is supposed to satisfy are fairly straightforward. Firstly, the addition of any two elements must also be an element of the field. The operation is symmetric, namely that x plus y is the same as y plus x. The operation is associative, which tells you that the order in which you perform addition is irrelevant. There must exist a special element called the additive identity or 0, such that adding 0 to any element would get back the same element. And finally, for every element x in the field, there should exist an element minus x. Minus x is just notation, right? That other element, I'm just denoting it by minus x, which satisfies the property that x plus minus x is equal to 0. Okay, so these are the properties that addition is supposed to satisfy. Multiplication is also supposed to satisfy a very similar set of assumptions. First assumption being that the multiplication, so if I write xy, this is basically the multiplication operation applied to x and y. Okay, so xy belongs to f for all xy in f, right? The second, so which means that the field is closed under multiplication. The next is again the commutative property, namely xy is equal to yx. The third property is in fact again parallel, it's the associative property, namely that if you multiply xy followed by a multiplication with z, that's the same as multiplying x with the product of y and z. Right? This is the associative property. Now, earlier with addition, we had a special element called the additive identity, such that adding that element to any other element gave you back the same element, right? Now again you have a multiplicative identity, namely there exists an element 1 belonging to f such that right? So there should exist a multiplicative identity element. We are just denoting it by 1, such that when you multiply any element x with 1, well, you get back x. Okay? And then finally, there is the question of the multiplicative inverse. For all x which is not 0, okay? Everything for everything except the additive identity, there exists 1 by x belonging to f. Now 1 by x is simply our notation for the multiplicative inverse, such that x times 1 by x is equal to 1, right? So in addition to the closure property, the commutative property and the associative property, first we say that there must exist a multiplicative identity, so an element which we denote by 1, such that 1 times anything is the same thing. And then for every element of the field which is not 0, there should exist a multiplicative inverse. So there should exist one other element such that x times that element is equal to 1. And so that other element, the multiplicative inverse, we are just going to denote it as 1 by x. Okay? So these are again the parallel properties that multiplication is supposed to satisfy. And finally, there is one property which in fact relates addition and multiplication, and that is the distributive property. That's why I have written D here. And that distributive property is as follows: x times y plus z, right? So the multiplication between x and the sum of y and z should in fact be xy plus xz. Okay, so if you define a set with two operations, addition and multiplication, that satisfy all of these properties, then we say that that set, along with the associated operations, addition and multiplication, defines a field. Okay, so this is the definition of a field. At this point, this is abstract. Any set that you can construct out of your head with associated operations that satisfy all these conditions would be called a field. Okay, so let me now give a few examples of fields. Right, the first example is of course Q. Q is a field, clearly. The set of rationals is a field. You can check that in fact it satisfies all of the properties that we laid out just before. As is R, even though we haven't defined the set of reals yet, well, R is also in fact a field. So is in fact the set of complex numbers. You have all been introduced to complex numbers before, right? So go back and check that with the standard definition of addition and multiplication between complex numbers, the set of complex numbers also defines a field. Okay, there is in addition several other fields that one could define. For example, there is a whole class of very special fields called finite fields, which if any of you takes a course in linear algebra, you will perhaps be introduced to. So I will not get into finite fields in this case, but this is something that if you don't know of, I would recommend that you do a quick search just to familiarize yourself with some of the terminology of finite fields. Similarly, you can talk about the field of rational numbers, rational functions. What are rational functions? Rational functions are essentially ratios of polynomials. Those of you who have done a course in signal processing or people who have studied the Laplace transform would be aware that the class of systems which are defined by rational Laplace transforms is extremely important, right? So, so the field of rational functions is also well defined. I invite you to go back and check that if I look at the space of all ratios of polynomials, that also defines a field. Okay, so these are several examples of a field. But if this is a definition that you are encountering for the first time, perhaps the most interesting thing to do would be to say, to derive several consequences that you have from just the basic rules that have been set in place for a field, right? Given the basic conditions that the operations defining a field are supposed to satisfy, there are several other very natural consequences that one can derive, right, from first principles, from the axioms of a field. So this, so I'm going to post a homework which will have many more of these, but at this point I'm just going to list a few and then I'll go through the argument for just some of them. Okay, so say x, y and z belong to F, where F is a field. Okay, in that case, what this lemma says is the following: x plus y equals x plus z implies that y equals z. This is the cancellation law. Right? So whenever you have x plus y equals x plus z, you can quote unquote cancel x from both sides, which leads you to the conclusion that y is equal to z. Again, this is not part of the fundamental axioms. It can be derived from the fundamental axioms. Right? Similarly, x plus y equals x implies that y is 0. Okay? So the only way x plus y can be equal to x is that y is equal to 0, which again you can kind of think of as cancelling x from both sides. But again, that this is true has to be proved from the axioms of the field. The third property of the lemma here tells that if x plus y is equal to 0, then y is in fact the additive inverse of x. Right? So this property tells you that the additive inverse is unique. Okay. 4 minus okay. So if you take the additive inverse of the additive inverse, you will get essentially the same element. So minus of minus x is in fact x. Zero times any element is 0. Okay. Okay. The sixth element, the sixth item of the lemma is also fairly intuitive, namely that minus x times y is the same as x times minus y, right? X times the additive inverse of y, which is in fact just the additive inverse of xy. Okay. And last for this lemma would be minus x into minus y equals xy. Okay, so if you multiply the additive inverses of x and y, that's the same as multiplying x and y. Okay, so again, these are all very intuitive properties, particularly since we come from the background of reals. So for us, from when you think of it from the standpoint of reals or rationals, these properties are all well obvious. However, I should remind you that the goal here is to prove these properties from first principles, given only the axioms I have, given only that f is a field, and so f satisfies all those conditions that I laid down in the previous slide, which was the 5 addition properties, the 5 multiplication properties, and the 1 distributive property. Those are all that I have at my disposal. All right. So I'm not going to go through all of these. So I'm going to leave, let's say, 1 and 4 as exercise, 1 through 4 as exercise. And maybe I very briefly talk about some of these. So let's say I want to look at number 5, right? I want to show that 0 times x is equal to 0. Okay, let us see how I would go about doing this. So what I could say is that 0 times x plus 0 times x by the distributive property is in fact, right, which since any element when you add it with 0 is also 0, you get this. So what we have shown is that 0 times x plus 0 times x is equal to 0 times x, right? Which by the first element of the lemma, the cancellation law, which I have left for you as an exercise, implies that 0 times x must be 0 via the cancellation law. Right? So again, I'm just writing this out to give you some examples of how these arguments would work. You have at your disposal the axioms associated with a field, which we have, you might want to write that down in one place, and you have to use those axioms to prove all of these consequences. Now let's look at number 6. In 6, we are saying that minus x times y is the same as x times minus y, which is of course the same as minus of xy. Okay. Now let us see again, this is really also a consequence of the distributive law. So what I'm going to do is say that xy plus minus x times y. I'm going to look at this sum, okay, which by the distributive law is x plus minus x times y, which is 0 times y, which is 0. Okay. Now, how do I know that 0 times y is 0? From property 5, which I just proved above. Now this implies that minus x times y is the additive inverse of xy, right? Because xy plus minus x times y is 0. So therefore, this must be the additive inverse of xy, which is essentially all I wanted to prove, right? What you wanted to prove is that So we have proved essentially that minus x times y is minus xy. A symmetric argument would show that this is also the same as x times minus y. Okay, so that is how I would prove number 6. Number 7. I want to prove that minus x times minus y is equal to xy. Okay, so now let us see how to go about doing that. So minus x times minus y, this is of course going to be equal to minus of x times minus y from property number 6, right? Now I apply the same property one more time to show that it's minus of minus xy, right? Which by property 4 is the same as xy. Or not point property 4, let's say result 4. Right? So I haven't done 1 through 4, I've left that as an exercise, but I've done a few to illustrate how it is that one would go about proving these. Okay, so usually these are all one line proofs, so they don't take a lot, but they are basically giving you practice on working with field axioms. Since particularly if you haven't worked with these kind of axiomatic frameworks before, this is an instructive exercise. Okay, so that is all I had to do when it comes to talking about fields. Okay, so next I'm going to talk about ordered fields, but I'm going to chop that and put that in the next video.